Hello. We are now going to talk about quite a different topic, which you would never have seen anything like in Java, and that's the notion of a pointer in C++. And to talk about a pointer, we'll start by talking about something called virtual memory addressing. So let's imagine we have a variable, and that variable, we'll just say, hypothetically, int x equals 10, okay? So we made some integer. And I'm going to think of that variable as living in a little box. And that box has 10 in it. Now this box actually is laid out and exists somewhere in memory. And in a place called virtual memory. Actually, it's not technically exactly what we have in our physical computer, but the operating system lays out as if we had this long chunk of memory to use. Okay, so every location in memory has an address. So I will say, for example, let's just say that this has an address of 1000. Okay, so the address is a number, and that tells me where to go. So it's like a reference, like we talked about before. That's what my memory address is. Okay, and an integer is 4 bytes long. So the thing after it in memory would have an address of 1004 to begin with. Now let's imagine that the thing after it in memory perhaps is a float. Or no, let's make it a double actually. Let's say double y equals 4.0. Okay, so doubles, you remember, are double precision. That means they're actually 8 bytes. So this little box has in it a 4.0. But it actually takes up 8 bytes of memory. So I'll make this box twice as big just to depict that. And the box after that will begin at address 1012. So 4 plus 8. And who knows what the type of this is or what it holds. But this is in a very long sequence of objects in memory. There's a bunch of stuff in memory. It starts before here and it continues after here. And we're just looking at a little part of it here. Okay, so x is 10. It takes up 4 bytes. And in this example, it happens to have address 100. The way that we get that address is by using a syntax as follows. So and x. So the and says, get me the reference, get me the address to x in memory. So this is the address. And x. Okay. And similarly, so that would be 1000 here. And then down here, if I said and y, that would be 1004. So it's wherever this thing begins in memory. All right, so that's virtual memory. So all the variables in your program are laid out, you can think of in this line here from top to bottom. And they each have an address. And who knows where they are? It's up to the operating system to determine that, actually. But we're going to see that the addresses are useful to know for various reasons. Okay, so let's actually write a little bit of code to put this into action. So let me do that exact kind of example. If I say int x equals 10, and then maybe I'll say, so remember, got to return 0, we're a, okay. What I'll say is printf I /n, so I'll put a line break after it, and x. All right, that's the memory address of x. So I happen to put this in a directory that I'm already in my terminal here. It's just a module, I call it module 7. It's in my home folder. So I'll say g++ out test.cpp. Okay, now if I say test, it gives us a strange number. Okay, and this is actually because we have the wrong type. Let me actually see something real quick. If I say, oops, I meant to say capital. So this hyphen capital W all, this will actually give me warnings that help tell me a little more information. So it says format integer expects type int, but argument 2 has type int star. There's that star again. We'll talk about that in a moment, but really what this is saying is, hey, you're actually printing out a memory address here. That's not just a regular integer. We actually use this type P, which stands for pointer. Okay. So now if I run it, I get this thing. So those of you who have me in 173 should recognize this. This is a hex code. This is the address and memory expressed in base 16 instead of base 10. And what you notice is this one has 1, 2, 3, 4, 5, 6, 7, 8. 8 times 4 bytes in it. So that means it's actually 32-bit. And so it just so happens that the virtual memory I have here is 32-bit, that I can address up to 4 gigabytes of memory. Some of you may see, especially if you're in Mac, you may see a longer number than this. I must be running 32-bit Cygwin here. When I was under Linux, this actually went further because our operating systems now mostly have 64-bit addresses for memory. So that's what you hear, the 64-bit processor. That means that you can go up to, what is it? So it should be about 16 exabytes of memory. And that should be enough memory to store every sentence that every human has said in the history of the universe. So that's a lot of memory, much more than we normally need. Okay, so here it looks like we're addressing up to 32 bits of memory. Actually, I can see that exactly if I say size of this. Let's go check that. Okay, it's complaining again, but oh no, actually I can go up to 64 bits on my computer. It's just I happen to not be even close to taking up that much memory here. Okay, so it says size of 8. That's 8 bytes. There's 8 bits in a byte. That means that the size of this memory address is actually 64 bits. Okay, so even I have the 64-bit Cygwin. I can go up to 64 bits of memory. But what you see when I print it out, the address, I'm not even close to using up that much. Okay. I don't have that much RAM on my computer. It turns out I have 32 gigabytes on this computer. Okay, so that's that. Okay, well, let's go back to looking at an array again. So I'll just comment this out. I'll keep it here so we can look at it, but let's make an array. So I'll say int r4 equals 1, 2, 3, 4. Why not? Okay. Or actually, let's make the numbers a little bit different. So I'll say 5, 2, 8, 3. Fine. Okay, so here, let's see what happens when I look at the address of the first element in the array. So if I say and array at index 0, and then let's look at the next element. And actually, I'll just do a loop. So I'll say for int I equals 0, I is less than 4, I plus plus. So we'll print out the address of each element in the array. So remember, the ampersand stands for address. I'm saying I want the address of the element in the array at index I. So let's see what this prints. All right, so first one is this address, FFFFCC20, okay, 20. Then we go to 24, then we go to 28, then we go to 2C. C is actually 12, for those of you who don't know or don't remember from hex. So the first address is this up to 0, then we add 4, then we add 8, and then we're at 12. So what this is saying is an array in memory. So maybe let's say that this is the beginning of an array. So I'll do this exact one. I'll say array, so I'll say int array 4 equals, what did I say it was? 5283. Okay, so actually arrays are laid out in memory in a contiguous fashion. So what it would be is this first box has a 5. The next box, I mean the addresses are slightly different here, but it's the same pattern. The next box would have the 2 in it. The box after that would have the 8. And the box after that would have the 3. The address of 2 would be 4 after the address of 5, right? Because ints have 4 bytes or 32 bits in them. So this is 1016, if I could do my arithmetic properly. This one is at 1020, and this one is at 1024. Okay, so arrays actually get laid out contiguously in memory. So what it means is if I start to do some arithmetic on the addresses, I can get results that reflect that. So if I go back here and I say, okay, let's look at a few things. So if I printf, let's say array at index 3 minus array at index 1 equals. So I'm printing, I'm actually having this in a string just to help me here. So if I do array at index 3 minus array at index 1 is equal to that placeholder there. I'll put a line break at the end. What I get is 1. Okay, that's because this is a 3 minus a 2, and that's 1, right? So that shouldn't be a surprise at all. But now if instead I say print, so if I want the address of the element at index 3 minus the address of the element at index 1, I'm going to say u. What this means is unsigned int. Don't worry about that too much. So this is array at index 3 minus array at index 1. Actually, no, let me make this an I. We'll see what we get. Okay, so I want the address at index 3 minus the address at index 1. Now before I run this, pause for a moment and see if you could think, what would this be? Okay, so let's look at it. Okay, so it's warning me, but whatever. Okay, this is actually going to give me a 2, which is interesting. From what I told you, I would have thought, hey, maybe that should give me an 8, right? Because this element at index 3 is actually 8 bytes ahead of the element at index 2. But C++ actually takes into consideration that these are ints, and so the addresses are expressed in factors of the size of int. And that's for convenience, because I want to know, it would be annoying if I had to say, well, this memory address is 1024 and this memory address is 1016. The difference between the two is 8. Now remember that the size of an int is 4, and divide that by 4 and you get 2. So C++ actually knows when you do this kind of arithmetic between two addresses of the same type, it knows that you want a stride between the two that's relative to the size. So let's just do another example here. Let's do, if we do array at index 3 minus array at index 0 versus the address of array at index 3 minus the address of the array at index 0. Okay, so array at index 3 minus array at index 0. So that's 3 minus 5, that's negative 3. I'm sorry, negative 2. Whereas when I ask you for the address at index 3 minus the address at index 0, well, that's 3. This is 3 integers ahead of this. Okay. So take a moment and let that all sink in, and then we'll continue.